I'm of equal badness to yesterday, I would say. Don't make me laugh. All right, so I will begin with a word of prayer. Heavenly Father, we thank you for this day. I thank you again for these students. Just ask you just bless this class. Help us to just understand more about your creation together today. Help the students to ask good questions as they think of them. And we just ask that you be glorified in what we do, Lord. In your name I pray, Lord Jesus. Amen. All right, so I have talked to you guys a little bit about factoring, not enough yet. So let me just do some basic examples in here to start with. Example 1. What if I'm up against something like x cubed plus 4x squared plus 5x? Can we factor this? And so, by the way, let me just say at the outset, our instructions for every single problem today are going to be factor completely over the reals, which means that if one of the quadratics cannot be factored, then we write prime and we go, okay, well that's that's irreducible. It can't be broken down. So here, what can you do? What would I do? Factor out the x. Woohoo! All right, so we've got x times x squared plus 4x plus 5, right? And what can I do? Why would I set it equal to 0, though? We're factoring, right? So we don't set equal to 0 unless you've got some kind of secret side plan on how to factor using setting things equal to 0, which I did once upon a time, but you guys don't want to be like me. So how about this? This right here, we could try to factor with completing the square. But when we do that, lo and behold, we get that works out to x squared, x plus 2 quantity squared plus 1. In other words, it's prime, right? So that is a prime polynomial. You cannot factor that unless you're allowed to use complex numbers, right? So for the purposes of today's lecture, we're going to say, nope, you can't do that. So in other words, factored. That's it. That's already factored over the reals. Are we good? Because it's the sum of squares. And so in order to factor this, I would have to pull this move. Recognizing that 1 is equal to minus I squared, so I can do the difference of squares there. So in order to factor it, I need complex numbers. Since we're not allowing complex numbers, no can do. But I don't want you to have to think about all that. Like, just in summary, when you complete the square, you get a square plus a number, it's prime. Because in order to factor a square plus a number, you have to bring imaginary numbers into play.
So you always want it to be the square minus that?
Yeah, sure. Let's look at another example. Like, what if we had x to the 4th minus 7x squared my bad. Plus 6. Let's see if we can do this one. Actually, this doesn't answer the question that you just asked. We'll get back to it, but what would I do here? What should I do here? This one's a little trickier. This one, I need to look at this as x squared minus 7x squared plus 6. In other words, make a substitution. Think of this as y squared minus 7y plus 6. It just made up the y. It came from the dark recesses of my imagination. So with that substitution, maybe you can see what to do. We can factor this, yeah? Put a y here, put a y there. How do you get 6? How is 6 and 7 related? minus 6 and minus 1, right? And okay, now we can undo the substitution, and we got what? X squared minus 6, x squared minus 1. Can we factor those? So it's not a square plus something, it's a square minus something. So that means we can use the difference of squares. Maybe I should write that down again. What's the difference of squares formula? A squared minus b squared equals to a plus b times a minus b, right? So we got that to work with. So putting that into practice over here, tilt your head, squint, and you can see what we got going on here is x plus the square root of 6 times parentheses x minus the square root of 6 times x plus 1 times x minus 1. Done. Once we're to all linear factors, that's as far as you can go. It's factored. Did I lose anybody on the x squared minus 6 thing?
I'm still confused as to how you got y squared minus 7y.
I made a substitution. So letting y equals to x squared. See, because it's a quartic to start with, right?
Yeah.
So if I have a quartic, maybe I can see how to do it if I can change it into a quadratic, because we know how to do quadratics is the idea. It's a trick.
Oh, so we can do that?
Yeah. If you can see the pattern. Now, can you always do that? No. Like if there's an x cubed, or if there's an x in your quartic, then you're out of luck. The only way this kind of chicanery works is if there's only an x to the 4th and an x squared. Like if there was an x and an x cubed, then that requires a deeper magic. So there you go. Factored. Woohoo! Any questions? So let's try another, yeah? Example 3. What if we're up against, I don't know, x to the 5th minus 10x cubed minus 37x. Oh, my bad. I think I lost track of my. That was supposed to be a 4. 37x cubed. Can we factor this thing? All right. So what should we do to start with? What? Factor out the x. Let's be greedy. Let's factor out the biggest power of x that we can, right? Factor out the largest power of x possible is what you want to do. Oh, you're fine. So what's the largest power that's common to all three? X cubed, right? We factor out x cubed. If we do that, what are we left with? We got x squared minus 10x minus 37. And then what? I mean, there's nothing more to do. X cubed just sits there. It's done, right? Stick a fork in it, whatever. But the x squared minus 10x, can you factor that? I can't factor that. What are we going to do? No, it's not prime. I don't believe it's prime, but let's find out. The square thingy. Yes, the square thingy. So yes, technically the square thingy. So x minus 5 squared, and then what do we do with the square thingy? We subtract the square of the thingy, right? Which is minus 25 here. And then 37, well, it's still there. Then what? Yeah, then we should clean it up a bit, right? So we've got x cubed, parentheses, x minus 5 quantity squared. What's 25 plus 37? Is it 62? So let's look at this as minus the square root of 62 squared. See, because then I can see, yet again, difference of squares, right? Which means we can factor it like so. X minus 5 plus the square root of 62, x minus 5 minus the square root of 62. Once you're to all linear factors, or to all linear factors and prime powers possibly repeated, you're done. So we're done, factored. Should we do another? Probably should do another. Let me think if I can think of a different pattern that we haven't come up against yet. All right. So here, I'm gonna pull a rabbit out of the hat here. You guys watch this one. X to the 4th plus 4x cubed plus 6x squared plus 4x plus 1 is equal to, why not? You can factor it. It's just x plus 1 to the 4th power. Or how about this? Example 5. If I have x cubed minus 3x squared plus 3x plus 1, or excuse me, minus 1, well, that's obviously x minus 1 cubed. Or example 6, what if I'm up against, oh, I don't know, 9x squared plus 6x plus 9. Well, that's just, well, three x plus 3 squared, right? I think. I could be wrong on that one. You better multiply that out and find out if I did something screwy there. I think I did that one wrong. Yeah, I should have put it 12. Sorry about that. All right, so the last 3 examples are completely inappropriate until I tell something to you, right? There's something I haven't told you about yet. There's a trick that I know that I haven't shared with you. Should I share it with you?
Yes, please.
Yes. So the trick is this, is we can put, let me make myself some room here. We put 1, 1, 1, 1, 2, 1, 1, 3, 3, 3, 1. So what I'm writing down right now is called Pascal's triangle. All right, so the way it works is you put 1s on the outside and you add the numbers above to get the next row. So like, for example, to get to the next row, I put a 1 on the outside. And what happens? 1 plus 3 is 4. 3 plus 3, 6. 3 plus 1, 4. Right? Yeah, sure. 1, 5, 10, 10, 5, 1. 1, 6, 15, 20, 15, 6, 1. We could go on, sure. Now, let me explain to you what these numbers mean. And what I'm sharing with you is called the binomial theorem. So I won't even talk about the top 2 numbers because they're kind of boring. But the third one, if I have a plus b, all right, and I square that, I get a squared plus 2ab plus b squared. That's what I was using for example 6. I was thinking of this as a squared, this is 2ab, and this is b squared, with a equals to 3x and b equals to 3. That was what I was up to there in that example. That was my underhanded trick. Now, this one, I can get a plus b cubed is a cubed plus 3a squared b plus 3ab squared plus b cubed. Now, in a college algebra class where I didn't allow you to have a formula sheet, this would be a much scarier topic, but it shouldn't be a scary topic to you because you have a formula sheet, which means you can write down the things I'm writing on the board on your formula sheet and make use of them if you want. Now, what's next? The next term, this row tells me a plus b to the 4th power is a to the 4th plus 4a cubed b plus 6a squared b squared plus 4ab cubed plus b to the 4th. Now, I'm going to write the 5th power on the other board over here, out of place, if you don't mind. A plus b to the 5th power before we just mindlessly write any more down, let's take time to understand the pattern. What's the pattern? What happens? You start with the highest power of a, right? And as you go across, the power of a lowers by 1 each time. 1 each time, until it's gone. At the same time, the power of b goes from 0, and it raises by 1 each time. If you look at any term, you always have the net sum of the powers of a and b being whatever power you're looking at. Like for a plus b squared, you have a squared power on a, 1 power b, 1 power on a, and 1 power b, so it's two total powers, right? There's always a total degree of 2, and if you look at the terms, the cube, look at this, 3a squared b. I've got 2 powers on a, 1 power on b. Did you see the pattern? Every term always has as many powers as the power we're looking at. So, so you guys just somebody told me what starts with a. I heard an a to the 5th. What comes next? A 5. Then what? A to the what? A to the 4. And then b appears, right? What comes next? 10? 10a, what? I said a cubed, right? B what? B squared? Plus 10? 10a squared b cubed. Now let me if you guys are not tracking where these numbers are coming from, let me show you where we are. We just got to this 10 is coming from this 10 right here. Right? That's the pattern. And it occurs to me the pattern may be off. You probably already got it, didn't you? Yeah, it's kind of, well, I'm not sure it can fit both, but I'll try. So then I get what? Plus what? Plus 5a b to the 4th plus b to the 5th, right? So now, I don't remember ever putting a 5th power on a test in college algebra. I'm just illustrating the 5th power because if you can do the pattern here, you can do the pattern for 3 or 4, which is more often like what I might try. Now, that's what I was using here. See? It's just the binomial theorem for my example 4 and example 5. I'm recognizing the binomial theorem. Now, I don't usually ask many factoring questions. Like there might be one question like this somewhere, but you know, by and large, these are, I don't know. If you see it, it's wonderful, right? If you see it, it's like, oh, I'm done. But if you don't see it, where do you even start, right? So it's a kind of nasty question in that regard. But it is something we should talk at least a little bit about because it's an important part of mathematics. The binomial theorem is a very useful thing. The binomial theorem is just what I'm writing. Pascal's triangle paired with the fact that you can expand a plus b to any power using the coefficients from Pascal's triangle. There's like interesting application to Pascal's triangle too. For example, what this 6 means it's like 4 choose 2. This is the number of ways you can choose 2 objects. Excuse me. Yeah. Number of ways you can choose 2 objects from 4 objects without repeating. Like if you've got A, B, C, D, right? Suppose you want to pick 2 things from there without repeating. How can you do it? You can pick like A and B, A and C, A and D, right? Those are 3 distinct choices. What else could you pick? You could pick B and C. You could pick B and D, right? And then what? Yeah, I heard and a C and D. Is that it? I think that's it. That's the only distinct groupings of 2 that we can pick from 4. That is why this thing right here is 6. This is, the meaning of that is what's called 4 choose 2 is equal to 6. Now, so the book, and if you take a course in statistics and probability here, you might talk more about this, okay? I don't test on that. That's for another course, all right? It's worth spending a second to talk about. And this is in the appendix in the book. Like the book has an appendix on the binomial theorem. I forget which letter. It's in the course planner. Any questions before I go on? Yes, no, maybe so. All right, so. So there are other special patterns. So the theme of today is either looking for the obvious thing to factor out, right? Using like the simple substitution idea like we did back in example 2. Of course, always looking for completing the square to see if that can break something up. But then there are a couple of other things that are kind of like the binomial theorem, but a little bit easier to track. And those are the difference or the sum of cubes formulas. So I should write those somewhere. How about here? You guys, anybody got what they want from there? Okay. Now, there is about a 50% chance whenever I teach this I remember the formula wrong. So I'm going to take a second and open up my camera and look at the formulas from last class after I corrected them. So, let's see here. Here we go. Now, the beautiful thing for you is you have a formula sheet, right? So you don't have to worry about being an idiot and remembering formulas wrong, right? So a squared. And then the thing is, when I make a mistake in there, they just start talking. And once people start talking, I've made a mistake, there's no hope. If people are talking, I can't undo a mistake. Now you guys are pretty quiet, so thanks. Yeah. I should mention, well, I guess I won't. Let's see here. A squared, I'll just keep that to myself. A squared minus AB plus B squared. So these are the difference of cubes formulas, right? And if you know about these, then you can factor particular cubics really easily, right? Let's try one of these on for size, yeah? Oh, you already got me? Cool, thanks. So let's start out with a really like basic one, all right? So example, I've lost my numbers.
No.
That seems wrong. 7?
It's 7.
It's that, okay, all right. How about this? X cubed, make it exciting, minus 64. All right, well, what is 64? 64 is 4 cubed, right? So I can think of A as X, I can think of B as 4, and I just substitute into that formula. And what happens is I get X minus 4 times X squared plus AB. What's AB here? plus 4x. And then b squared is 16, right? Are we done? Have we factored it?
You're never done.
You're never done? Well, that's kind of depressing. No, it's not. I love math. Let us never be done.
Can I ask a question to the class?
Oh, man.
Is anyone
This
in
feels
here trying to be a
dangerous.
math major?
How dare you?
I think I'd rather kill myself. Amen, brother.
He has insulted your future major. What have you to say?
Not the future math major. She is. You should talk to Leah.
Yeah?
She's
At
the
degree.
future math
This class reminds me of high school. That's why I hate it.
Since we're being brutally honest, just kidding.
You're welcome.
It's okay.
I respect this class like that. Mr. James Cook class I look forward to every week.
Well, thank you.
I like math, but
I sense some sarcasm.
I actually do love this class.
Okay, good, good,
I
good.
love you. I like you, not the material.
Yeah, I like you as a teacher, but just.
I understand. You feel the same way about this class as I felt about, like, literature.
I look forward to your shirt too.
No, you don't. There, actually, I retract that. There's no earthly way you guys hate this class as much as I hated, like, second semester literature. Because I hated it with a pure and unbounded hatred. But anyway, okay, so where was I? Completing the square will tell us whether or not we can factor that, right? So, by the way, I'm glad you're here, but if you don't need to be here to learn, like, you don't have to come to class. Like, I don't take points off, you know that? Like, if you don't show up for class, like, I don't take points off. But it is hard to take the quiz when you're not here, right? So there's that. And I also don't give make-up quizzes, so there's that. But I also tell you when I'm going to give you the quiz, so there's that. Just saying. And if you're pretty much sure that you can work out the rest of the material in the course and you want to just come and take the final or something, you probably could work something out. But anyway. All right, so you can come talk to me in office hours. We can talk. Let's see here. So x plus 2 quantity squared minus 4 plus 16. What do we got? See, now I'm going to have to edit all that out. So I'm completing the square, right? We take half of the x coefficient, we add it, we subtract the square of the thingy again, right? And that leaves us with what? X plus 2. Listen, guys, before I was a math professor, I was a math major. And like, I had this conversation with like hundreds of different people. What's your major? Math. I'm a double major, actually, also in physics. And it always responded with why? Like, it's just the same conversation over and over and over again. So I am well aware that, you know, by and large, people do not like math. So my goal here is not to make you to hate it more. I mean, I'd like you to like it. Consider liking it. Don't make your children hate it before their time. Yeah. The quizzes are open notes, yeah.
They are?
Yeah. Did I not say this?
The last one was open.
Okay. Yeah. All right. Let us continue. All right. So, listen. What does this mean? This means we're done, right? It's prime. And I've got some good news. Like, let's try another one here. Example 8. How about 8x cubed minus or plus 100? So this one, we need to use our imagination a little bit, right? This is 2x quantity cubed plus the cube root of 10, or excuse me, the cube root of 100 cubed. So that's a thing. If you can write a number as the square of the square root, you can also write it as the cube of the cube root. If you want to make something become a cube, you just got to use your imagination. And also, cube root is friendlier because you can take the cube root of a negative number. It's fine. It's not imaginary or anything. And then we just use the sum of the cubes formula, right? So that's 2x plus the cube root of 100 times x squared, which would be 2x quantity squared, minus 2x times parentheses the cube root of 100 plus the cube root of 100 squared. And so I'll clean that up just a bit. That's 2x plus the cube root of 100 times 4x squared minus 2 times the cube root of 100 times x plus the cube root of 100 squared. I'll just leave it like that. So let me explain something. So for a cubic, if you guys don't mind, let me travel forward in time a bit and just tell you what does y equal x cubed minus 64 look like? It's a what? It's a cubic, right? We haven't really talked about that, but just hang with me here for a second. It looks like a sneaky snake, and so basically it looks like that. All right, and guess what? Y equals x cubed plus 100 looks like. Well, it's also a sneaky snake. I don't know. It looks something like this. Whatever. That's y equals 8x cubed plus 100, roughly speaking. All right. So if you look at these two, how many zeros do they have? So this is something we need to talk a lot more about in this course, which is the so-called factor theorem, that whenever you have a 0 for your polynomial, you have a corresponding factor in the factorization, right? But if you only have one factor, you can only have one real, if you only have one real 0 for the graph, you can only have one factor. So you see, the fact that there's only one place it crosses the x-axis here, the red one, right? That is corresponding to the fact that there's only one place where you have this kind of factor up here, right? 4 is the only place that y equals x cubed minus 64 crosses the x-axis. All right? Likewise, there's just one place where the blue one goes across, right here. Where does that point, if you want to figure it out? You'd set this number here, this thing here equal to 0 to find that. We'll get back to that later. But my point to you is just this. With these cubics, anytime you use the sum of the cubes or the difference of the cubes, you can count on the fact that what you're left with, it'll be prime. So yeah, I completed the square here to show you that it's prime just explicitly, but I'm not going to do it here. I don't even need to. I can tell you before the fact without even completing the square, which would be a pain because of the numbers here, right? I can tell you this is prime. The reason I know it's prime, again, is because it only has one 0, which means it only has one linear factor. Are we good? So listen, we will do more factoring next class. I think we always need to do more factoring. But the other topics we have to cover before the test are like ellipses and circles and hyperbolas. So we'll get to those as well. But anyway, let me turn off the camera and then I'll let you guys get to work.